Now that we know how to implicitly differentiate equations, we can use that ability to solve problems that involve related rates. So, what are related rates? Well, here we're going to look at how two or more variables change with respect to time. That's a rate, right? And we're going to take a look at how two rates affect each other. So we're going to find an equation that governs the relationship between these two rates. And to find that equation, we need to use implicit differentiation. So here's my question. Here it is. Okay. So this is a classic problem, ripples in a pond. So the question is, a rock is dropped into a pond causing ripples around it. The radius of the outer ripple is increasing at the rate of 6 inches per second. At what rate is the area of the circle of turbulent water increasing when the radius is 18 inches? What is this question exactly asking us? Well, from experience, you know that when you throw a rock or stone into a pond, you see ripples, circular ripples around it, coming out of it, right? Okay, so now the question tells us that at a certain point in time, the radius is 18 inches, and with this ripple here, the radius of the circle always increases at the rate of 6 inches per second. And it's asking us to find the rate at which the area increases with respect to time. So with any related rates problem, we first have to identify the variables and then find the equation that tells us the relationship between these two variables. So our two variables are the radius and the area. And what are we given? Well, we're given that dr over dt. Now think about this, dr over dt. Why is dr over dt? Well, it's because the radius is changing with respect to time. The rate at which it's a rate. So that's going to be 6 inches per second. Right? The rate at which the radius increases is 6 inches per second. And we want to find dA over dt, the rate at which the area changes. We don't know this, but we want to find this rate when the radius is 18 inches. There you go, 18 inches. Why did they give us this piece of information? Well, it turns out that although the radius increases at a constant rate, the area does not. The area does not increase at a constant rate, and in fact, it depends on the size of the radius. And we'll see why. Okay, now coming back to here. So our two variables are the radius and the area. And, okay, so we want to find the equation that tells us the relationship between these two variables, and we know that since these are circles, the equation is going to be the area is equal to pi r squared. Alright, now we're going to implicitly differentiate both sides. And that's going to give us dA over dt is equal to 2 pi r, we have to use a chain rule here, so it's going to be 2 pi r dr over dt. Okay, so what does this tell us? It tells us that the area, the rate at which the area changes, depends on two things. It first depends on the radius, and it also depends on the rate at which the radius increases. Okay? So, well, we have the equation here, so why don't we just plug it in and see what happens. So 2 pi r is 18, and the radius is 6. And that's going to give us 216 pi cubic inches per second. Square inches. Square inches per second. So 216 pi square inches per second. And that's the rate at which the area changes only when the radius is 18 inches. Now, why is that? So, we see here that we have an r in d over dt, and that's going to mean that the area is not changing at a constant rate is changing at a rate depending on r, and in fact it's going to be increasing, right? The rate at which the error increases is going to be increasing. Here, let me show you. So when the radius is, say, 2 inches, dA over dt is going to be what? It's going to be 2 pi times 2 times 6, which is going to be 24 pi square inches per second. Whereas when the radius was, in this case, what was it? When the radius was 18 inches, dA over dt was 216 pi square inches per second. And during both of these times, the r over dt was equal to what? It was equal to 6 inches per second. This is an r here, the r over dt. Taking a look at this, what can you tell me? Well, the radius changes at a constant rate, whereas the error does not change at a constant rate. In fact, it's increasing. That's what I mean by increasing. The rate at which the area changes increases. And does that make sense? Well, let's think about it. If we have ripples here, and say each of these ripples are 1 second apart, so during, say, t equals 1, the ripple is this side. During t equals 2 seconds, the ripple is this side, and during t over 3, the outer radius, the outer circle, was this size. So we see from t1 to t2, the circle increases by this area. Okay? This much. Alright. But during the next second, from 2 to 3, circle increases by this much. I can't tell the difference now. But anyway, probably you should have used a different color. But alright, there you go. So, during, from T1 to T2 increases by this much, and from T2 to T3 increases by this much. And you can see that indeed, the rate at which the error changes does increase, right? This area is greater than this. And that's going to be true, because we see so here, but the reason is because A depends on r squared and not r. A is proportional to r squared, and A is not proportional to simply r. So that's why. And when we differentiate it here, we still have this r term here. So when r becomes larger, the A over dt, the rate at which the area is increasing, becomes larger. Okay. That's the point I wanted you to understand. That's why I spent so much time on it. Okay. Now that we've talked about this, I'm going to give you another problem. It's going to be similar, but only different in one minor thing. So the second question that we're going to work on is air is being pumped into a balloon at the rate of 3 cubic inches per minute. Now, what rate is the radius of the balloon increasing when the balloon is 32/3 pi cubic inches? So, what's the question asking us? Well, we have a balloon. The question didn't say, but I'm telling you that the balloon is going to be spherical. So here's a balloon. There we go. And we're pumping air into the balloon at the rate of 3 cubic inches per minute. What is that equivalent to? That means that the volume of the balloon is going to be increasing at 3 cubic inches per minute. Right? Okay. What else does the question tell us? Well, it wants us to find the rate at which the radius of a balloon is increasing, and tells us that it wants us to find that rate when the volume is 32/3 pi cubic inches. When the volume is, okay, so instead of telling us the radius, it's telling us the volume. And we'll see how we can deal with that later. So, first step is to identify all the variables and the quantities that are given to us. So the two variables here are the radius and the volume. right? So what's given to us? Well, this is something. So we're told that the volume increases at a rate of 3 cubic inches per minute. And the question wants us to find dr over dt, right? The rate at which radius changes when the balloon, so our volume is going to be 32/3 pi cubic inches per minute. Sorry, cubic inches. Right, so our volume is going to be 32/3 pi inches. Right, so now we have to find the equation that tells us how these two variables relate to each other. And that's going to be b is equal to, well, if you don't remember, it's okay, I'll tell you it, 4/3 pi r cubed. So now that we have this equation, let's implicitly differentiate both sides. dB over dt is going to equal 4 pi r squared dr over dt. Alright? Okay. So this equation tells us that the rate at which the volume changes depends on r, actually depends on r squared, and also on dr over dt. Okay? So let's plug everything in. Well, let's see. We're trying to find, in this case, dr over dt. Okay, we're trying to find dr over dt. We have dv over dt, but we don't have r. Is that a problem? No, it's not a problem. Well, because we know the volume, and using this equation we can easily find the radius. So let's do that first. So 32/3 pi is going to equal 4/3 pi r squared. Okay, this cancels out. This cancels out. Bring this over. 8 equals r cubed. And then so it's an arrow here. R is going to equal 2 inches. Okay, so let's plug everything in. Alright, so we know the volume. The volume is going to be dr over dt is 3. 4 pi r we know is 2. 2 squared dr over dt, so this is going to be 16. So 16 pi, bring it over, under 16 pi, 3 over 16 pi is going to be the rate at which the radius changes. Okay. So in this case, we see that whereas in the previous example, the radius was increasing at a constant rate, in this case the volume's increasing at a constant rate. And here it's the radius that's changing. Here the radius is changing at a variable rate. If we solve for dr over dt, you get to notice something. So let's do that. So we're going to, I know you can see this, but I'm going to bring the paper up later. Let me just do this first. There you go. There you go. I wrote this thing down. dv over dt times 1 over dr d pi r squared equals dr over dt. So what does this tell us? Well, here we see that r is in the denominator for the equation to solve for dr over dt. So that tells us that as the radius increases, dr over dt is going to decrease, and dv over dt stays the same. Does that make sense? Well, it does, right? Because for every additional volume you add onto here, the radius has to increase only by a smaller amount. Right? And it does, right? Because say you're here first. For every additional volume, so say this is t equals 1 minute, t equals 2 minutes, t equals 3 minutes, going to be closer. Right? This thing here is going to be smaller than this thing here. I don't know if you can see that, but anyway, the radius is increasing at a smaller rate. Okay, and that's because of this equation here. Okay, so that's just something to notice. So let's review now. Okay. So in this case, what do? We first identified the two variables. We wrote down all the givens. We found that we wanted to find d over dt. We wrote the equation that governed the relationship between r and v. Using that, we implicitly differentiated both sides, and then we plugged in everything we had, but we saw that we didn't have r. That's okay. We solved for r using v, and then there you go. And then we found d over dt. Good. So this is just something I wrote. So this is what we did. For any related rates problem, you want to first identify the variables and quantities. Once you do that, you have to find the equation relating the variables, which in this case was this one, right? And then you implicitly differentiate both sides. Once you do that, you substitute everything back into equations. If you don't have the values for some of the variables that you need, such as in this case r, you can solve for them using what you're given. And once you substitute everything back in, you solve it, and then there you go. You find your related rate. Hopefully that wasn't too bad. We have 4 more examples to do in the following 2 lessons. So see you there.